As you've seen, solving nodal analysis equations involves matrix inversion. It is not just nodal analysis. Solving any system of linear equations involves matrix inversion. So in this lesson we will look at matrix inversion methods very briefly. Okay, it's assumed that you know all of these things from high school algebra. Okay, otherwise you can always refer to a standard textbook for this. I will go through it once just so that for the small circuits such as a 2 node or a 3 node circuit, you can invert matrices quickly and find the complete solution. Okay. In general, if you have a square matrix A, the inverse of that is 1 over the determinant of A times a matrix of cofactors. Okay, I won't go into the definition of all of these things. I will just show the results for a 2 by 2 and 3 by 3 matrix. Okay, now this symbol of course means the determinant of A. Okay, now let's take a 2 by 2 matrix. A equals A11, A12, A21, A22. Okay, and the inverse of A is 1 over determinant of A, which I think you already know how to calculate. It's the product of the diagonal terms A11 times A22 minus the product of the off diagonal terms A21, A12. Times the matrix of cofactors, which is very easy for a 2 by 2 matrix. Okay, so all you have to do is swap the diagonal elements, that is A22 comes over here and A11 goes over there. Okay, so you simply interchange the positions of these two, and for the other two you retain the positions but negate the values. Okay, so here and here you have minus and minus. That's all. Okay, so now you can go back to the example we had earlier. Okay, which was we had a G matrix which was 3 by 2 minus 1 minus 1 5 by 4 millisiemens. So the inverse of this is 1 by the product of these two, which is 3 by 2 times 5 by 4, and each of them is millisiemens. So the unit of this is millisiemens square minus the product of these two, which is just 1. Okay, millisiemens square, and I have to swap the diagonal elements. So I get 5 by 4 millisiemens over there, 3 by 2 millisiemens over there, and this minus 1 will become 1 millisiemen, and the other minus 1 also becomes 1 millisiemen. Okay, and this whole thing will be equal to, if I simplify this, I get 7 by 8 millisiemens square. So I have 8 by 7, and 8 by 7 millisiemens square times all of these entries, which will give me 10 by 7 kilo ohms. I get this kilo ohms because I have millisiemens divided by millisiemen squared. Okay, eight by 7 kilo ohm, 8 by 7 kilo ohm, and 12/7 kilo ohms. Okay, and this is what I used. I multiplied the current source vector with this to get the node voltages. Okay, so for a 3/3 matrix, you can similarly calculate the inverse by calculating the determinant of the matrix and various submatrices. You can look at any standard textbook for this. Only one other thing I will mention is what is known as Kramer's rule. Let me take my nodal analysis equation. G times V is I, and I'll assume that. So I'll assume a 3/3 matrix which corresponds to a 4-node circuit, which is described by 3 KCL equations. And in general, there will be 3 non-zero elements, I1, I2 and I3, okay, which consist of total currents pushed into each of the nodes. They may not correspond to the values of single current sources, but they correspond to the total currents being pushed into nodes 1, 2 and 3. Okay. Now this Kramer's rule is convenient when you are not looking to solve for the vector completely. So let's say you want only one of them, right? Let's say V1. What you do is V1 turns out to be the ratio of two determinants, and in the denominator we have the G matrix itself, G11, G12, G13, G21, G22, G23 and G31, G32, G33. And in the numerator, that matrix is basically this G matrix, but with one of the columns replaced by the right hand side. Okay. In this case, we want V1, so the first column is replaced by the right hand side vector, and the remaining two are the same as before. Okay. Similarly, if you wanted V2, we would have G here, and in this the second column would be I1, I2, I3. Okay. So similarly for V3, you would take this right hand side vector, put it in the third column, take the ratio of that determinant to the determinant of the G matrix. Okay. So this is also sometimes useful. Again, for hand analysis, 3/3 is the most complicated that we would consider. Okay. For all other cases, if you have to solve for larger circuits with dimensions more than 3/3, you use a computer. Okay.